Okay, kiddos. Here is your introduction to simple harmonic motion and oscillations, periodic motion, that kind of thing. So, in physics, we talk about simple harmonic motion because it's just sort of that's the way the universe works in a lot of situations. So we can look at ocean waves, from the side, and they're going to look something like this until they get close to shore, and then they're actually going to break. We could look at the amount of daylight as the year goes on, right? And in summer we have a lot of daylight, and in winter we don't have a lot of daylight. So these are looking sinusoidal, which is related to simple harmonic motion, and I'll get to that down below, real close. In physics, however, we talk about this. So the two systems that are sort of simple to study and exhibit simple harmonic motion are one, the mass on a spring, so we have a spring and a mass hanging from it, and then the other is a pendulum, so we have the bob and a string attached to the ceiling, and it will swing back and forth. So that's not really new to you, right? But there is more to it. So here we go. There are three different ways that I like to describe simple harmonic motion. So this is what we're looking at, simple harmonic motion. What does that actually mean? Sure, something moves back and forth, and that's correct, but there's more to it. So first of all, if we look at position as a function of time, so we got position as a function of time, the graph will look sinusoidal, meaning like a sine or cosine graph. So if you've had trigonometry, you'll know that the graph of y equals, let's see, this is starting at 0, so it'd actually be sine of x. So y equals cosine x or y equals sine x. These would be what we call sinusoidal graphs, meaning they're these nice smooth curves up and down with some middle point. They're symmetric about the time axis or the x-axis, and they look something like this. So simple harmonic motion, if we graph position versus time, will look like a sine or cosine graph. So that's one way to describe simple harmonic motion. The more technical definition of simple harmonic motion is that the restoring force is proportional to displacement from equilibrium. So I'm used to saying that and having students kind of tune me out. It's a bunch of words, but let's talk about this. What does this actually mean? So from the ceiling, there's a spring and there's a mass. And I did this little dotted line here. We call this equilibrium position, meaning where the spring would be if there's no mass hanging from it. Actually, let me rephrase that. Here's the mass just hanging there, all right? So while it's at rest, we can call this equilibrium position. And the little arrow here, this is what I meant to talk about when I drew this, and the little arrow means if we were to sort of set this thing in motion, so we hit it or we pull it down and release it, it's going to move up and it's going to move down. And the amount that it moves up and then it moves down would be the same from equilibrium. So this distance would be the same as this distance. So anyway, we call this equilibrium position. And when we talk about restoring force, we're talking about there's a force that brings the mass back to its resting place. So if the mass is at rest and we pull it down to here and we let it go, there's a force pulling it up. If I were to lift the mass up to here and then let it go, there'd be a force, gravity, pulling it down. So this restoring force is the force that brings it, we'll just be general here, back to equilibrium. How do I spell that? Equilibrium. That's the restoring force. And when we say it is proportional, we mean that as the displacement from equilibrium, so we should talk about that, displacement. What's displacement? We know that from earlier in the year. Displacement is how far it's moved. So here's equilibrium, displaced from equilibrium or displaced from equilibrium. So the more you pull it away, the more the restoring force is. That's what this proportional thing means. So if I were to pull this far away, and let's say it's a force of 10 newtons pulling the mass back, if I were to double that distance, it would be 20 newtons pulling it back. So this is what we mean by restoring force is proportional to displacement from equilibrium. So any situation where this is true, the thing's going to move back and forth, it's going to oscillate, and its position time graph will look like this, and we call that simple harmonic motion. And what's our last thing here? So we're going to try this in class, because I always explain this, and I'm not sure it really sinks in. What I say here is movement looks like side view of something rotating. That's pretty vague. So what we're going to try is there's a flashlight, and there's something that moves, such as we have the physics wheel, and what I have here is, let's say, some object that's taped to the side. So as this thing moves around, let's say this is moving at some constant angular velocity, right? And we're shining this flashlight, and what we're looking at here is the shadow. And so right here we'd have a shadow of the object, and it would be right here. And as it moves around, the shadow would move down, and then the shadow would move back up, and then the shadow would move back down, and then the shadow would move back up. And this motion is actually simple harmonic motion as well. So it'd be going fastest here and slowest here. It's not this even tuk, 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 tuk. It's more of a woo, 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 if that makes any sense. So not like this, if we were looking at position versus time, but there's the woo, woo, woo. Yeah. Okay, next slide. So let's watch this. Hey, let's watch this. Okay, so here we have mass on a spring, and it's spinning around just because of the string, so we will get rid of that. Spinning motion. It is sitting at equilibrium position here. So if I were to take all the weight off, the spring is about that long, and when we put the weight on the spring, it goes to about that length. And then if I displace the mass from equilibrium and then release it, it oscillates back and forth. So that's the voom, voom, voom. Cool. All right, and let's see. There's a lot of information on here, so I think we're going to just put this on pause. We're going to call this part 1, and then we'll resume at part 2. Okay.